welcome. Thank you for being here. I'm Leo Kobayashi. I'm an emergency physician. I work with Dr. Hayward, and she invited me to give this talk. This is a slightly different, more engineering type talk, but there's a specific climate change health payoff, if you will, at the end. And so I think it might be of interest. I get to be the first speaker in this part. Jed Thorp is here from Clean Water Action. And so I get to introduce the problem and he gets to fix it. So it's actually a good arrangement. So very good. All right, and so we'll be talking about this project. It's currently based out of Brown Design Workshop. It's an engineering space on the east side. It's in the engineering department. It's a resource that's open to all. You can literally walk in, sign up, and start using CNC machines and lasers and all sorts of interesting engineering developmental devices. And I have no conflict of interest with respect to BDW. I do want to mention the team. Also, Joanne couldn't be here because she's, I think, presenting something as part of her senior thesis. She was instrumental in getting this project running, so Joanne Liu, and she's pre-med, so we'll be seeing her soon. Aurora, Hannah, Natalie, they're undergrads, and they were instrumental in the work as well. Ben, John, Jerry, and Louise, and Chris. They help run the BDW, and they are the individuals who keep the place running and make it work. So, and then just me. The work has been sponsored by some funding from the Sustainability Office at Brown. And they actually, for your interest, if you haven't heard about this, they do have a sustainability seed grant program. And so you can apply for up to, I think, 20 to 25K. It's a relatively short application, rapid turnaround, and they're quite accommodating and interested in proposals. So it's definitely worth looking into. We actually got 1.5. We got 20 for the first year and a 5K rider. And then we've also been supported by Hazeltine funds from the Department of Engineering at Brown. Okay. I do have some disclosures I need to mention. The work that I'll be discussing, it pertains mostly to 3D printing and its consequences and how to mitigate them. But in terms of getting to the 3D printing, myself and some of my teams have been involved with the funding from the opioid Cobra downtown. We also, as mentioned, sustainability grant. I do have a small company on the side. I will not be peddling any of my products here, so rest assured. But it does result in some biomedical device development and engineering and 3D printed waste. So I do need to disclose that. And then that particular company does have Commerce Rhode Island support. If you're looking into starting a small business, they are a great resource, and you can speak to me separately about that as well. Okay? Good. So just a quick show of hands. Who has a 3D printer at home? Excellent, good, all right, okay. And have most of you 3D printed or been involved with some 3D printing process? No? Okay, all right. I mean, it's, and I'm not like some tech bro person, but it is truly an amazing technology. And if you've seen it work and if you've seen what it can do, it's quite revolutionary. They have one on the International Space Station because it's such a resource that can, create tools and materials that you otherwise would have to, source in other ways. There are different types of technologies. I'm not going to bore you to tears with all the details. There are 3 primary types, and we'll be talking about the fused deposition modeling approach, which is FDM. And the idea is that it takes spools of plastic filament. They're approximately 1.75 to 2.85 millimeter diameter. And then it basically puts it in this machine. It heats up the plastic, and it literally layers the material down. It just literally, just lays down plastic in layers. And it creates a 3-dimensional shape by moving either the gantry or the extruder head. There are other types which are much more involved. There's SLA and there's SLS. I'm not going to get into that because A, I don't do them, and B, they're harder to recycle the materials. They tend to be a little more toxic as well. So just some examples of 3D printing. So jewelry, architecture, that's actually a person standing next to a 3D printed object. So it's not just small scale, prototyping. This is like, in large industrial scale. We're now, not we, but the world and individuals are 3D printing enclosures and housing. And so this actually might have an impact on climate change as well. Temporary shelters that you can 3D print quickly. And then there are biomedical applications. That's a model of a titanium printed mandible that was replaced in actual patient care. And so it's coming. It's quite versatile. The issue that results from it is that 3D printing, there are a lot of drawbacks to them. It can be slow, it uses electricity and energy, and then the specific aspect that we'll be talking about is just the sheer amount of waste that comes out of it. The original intent, as far as I'm aware, for 3D printing was for rapid prototyping. And the idea is that instead of CNCing something out of wood, metal, or like ordering it from some specialty shop, you can create it in a CAD program and then make it and print it and have a piece or a device within hours. There's the advantage of having that rapidly done, but then there's the disadvantage that you basically iterate through multiple prototypes, and a lot of them fail, or they're just not the right size, shape, or specs. And so then you end up creating waste. The dirty secret behind FDM, filament deposition modeling, 3D printing, is that they claim that a lot of the materials that are used, the most common is PLA, which is polylactic acid. The claim is that it's compostable and biodegradable. It actually is used in biomedical implants and other drug delivery systems, so it is quite biodegradable. The problem is that when you have them in bigger quantities, like all the supports and failed prints and the prototypes that you don't use, they can be composted, but it has to be under very specific conditions. It has to be in a moist environment at pretty high temperatures. And so if you put it in a landfill environment, it's not going to decompose. It's just going to stay there just like any other plastic, and then it's going to degrade and turn into microplastics and nanoplastics. Because of this context, we were hoping to come up with a pipeline, and this will get faster as I go through the rest of a lot of pictures. But we were hoping to create a pipeline that can help address some of these issues and downstream consequences of 3D printing. So these are some of the things that I've worked with. None of them have to do with my company per se. We had a system where we rapid prototype a system to monitor naloxone containers in public settings so that people can access the containers, and then the owner managers, those units can be notified using a cellular IoT. We had to rapid prototype the container housing and the circuit holders, and we've had them deployed. We completed a study, it was published last year, and it generated a little bit of rapid prototyping waste. This is a hyperspectral imaging system that we are borrowing from the NIH. We had to cobble together and 3D print some housing materials to contain, house, and support the camera systems. So, and if I could, make this out of duct tape, or I could, like get a CNC machine and spend a lot of money, or I can 3D print it. And so this is quite, fast. I mean, printing that enclosure on the right probably takes about an hour and a half. And, you can just shape it, do it on your CAD program, and just get it done within like a few hours. We have a system that tracks medical equipment, like interpreter devices, laryngoscopes, ultrasounds, in the ED, and we needed a housing to house the cables and make it look nice in the clinical environment. And so I had to, 3D print on that as well. And then for medical education and training, we've created these 3D printed housings so we can facilitate central line training. And so this is something that I was working with the ultrasound department in the ED. So, there are pretty specific applications, and I literally make, it's adapters and stuff for my condo. I mean, as mentioned, it's not restricted to biomedical equipment. I mean, people do all sorts of stuff with this. We can also make toys. So this is the process that we've come up with. That's the bank of 3D printers at the BDW. There are currently, I believe, 11 printers, and during the school year, they're basically continuously printing, and they go through a large amount of PLA. Joanne, the medical student, pre-med student, who was involved with this project, she helped set up the collection bins underneath. And so I'm going to walk through the process, and then I'll show you pictures. The idea is that we collect the materials, the waste prints, and we actually get bucket loads every week, unfortunately. We sort them. We have to filter out and take out the materials that are not PLA, like other materials. And then we shred them. We have a precious plastic shredder that was purchased with sustainability fund grants. And then we have a grinder. It's an industrial grade grinder that actually grinds up the plastic. And then, it goes through that process. On the waste is just some examples of waste print. And then the middle or the intermediate step shreds, and then you get the grinds, which are smaller. And then once we get the grinds, we put them into an extruder that heats it up to about 400 degrees Fahrenheit. And then it extrudes it on this nozzle over here. And that's basically just like a nozzle that tries to extrude plastic material in semi-gelatinous form. And then It basically creates a strand. We spool the strand. Another dirty secret is that we have to redo the process because typically the strand consistency is inadequate on the first pass because of all the contaminant materials and the heterogeneity of the material. And so we have to pelletize it. We basically create, we cut the strand again into pellets and then re-extrude. And then we do final extrusion and spooling. It takes approximately, at this point, on a single pass, path extrusion process, it takes about an hour per kilogram. So it's not very efficient. And we're looking into creating parallel streams to try to improve the output, but it's not very time efficient currently. We've been doing quality control and testing. Dr. Manfredi at the BDW is the sustainability biomaterials expert, and so she's going to be helping test some of these, some of the output. Now, the thing is, once we reprint using this PLA, that can go back in the stream. So it becomes truly a circular process. I mean, like if you have like something that's burnt or like, burnt, if it's contaminated or dirty, you can't. But if it's reasonably clean, failed print, you can just toss it right back in and just go through the entire process. So that's the bank of printers. That's some examples of print material that gets repurposed by us. That's the shredder, and then that's initial stage shredding. That's the cutting blade or the grinder mechanism, and then it creates grinds, which are probably about between 5 to 6 millimeters per particle. And then it goes into this contraption, which Joanne also helped to build, and it goes into the extruder. It goes over that multiple fan thing to cool down. It gets stretched a little bit by the pulling mechanism. It gets spooled. We keep track of quality control in terms of filament thickness because that's unfortunately, I guess it's germane because the 3D printers are very finicky about filament thickness. And we've generated some filament. And then, it looks like it's done, but then as mentioned, we have to pelletize it, we have to cut it again, so we've come up with this 3D printed, ironically, mechanism that helps pelletize. And then we put it through the pelletizer, we get pellets, and then we put it through the extruder again, and then we get filament. And then it goes into our dedicated 3D printer. We've been working mostly with 2.85 millimeter filament because when we try to extrude at 1.75, there are enough contaminants and other materials that it typically tends to jam the smaller extruder heads for the 1.75 millimeter printers. The advantage is that the 2.85 prints much faster. So if you're trying to make something big, it'll print about 5 times the speed or more. And that's just an example of a quick print. You can see that it's very coarse looking, and that's because of the size of the filament. It's intended to be a true, quick and dirty, hopefully not dirty, but quick, rapid prototype. We've been looking at alternative processes such as baking the granules. And so instead of putting it through the extruder and using all the energy and spooling and going through that, you can put it in a baking tray and then bake it. And you just use an engineering grade oven. You put in these baking sheets, courtesy of Home Goods, and you get all these multicolored materials. You can, they're reasonably spec'd out in terms of thickness, and then you put in a laser cutter, and you can get material that you can use for various projects. So instead of buying a PETG sheet or something from MasterCar, you can just go to BDW, get these sheets, and use it for a project. These are some of the results, and so this is a print with new raw, commercial PLA 1.75. This is a print using 60-40 mix. Oh, and I do need to mention this. When we repurpose the PLA, we have to mix in virgin, new PLA pellets because the recycled material just typically loses some of its characteristics, and so we have to mix it in. We've been experimenting with the ranges from 50-50 to 70-30, and we're trying to tweak the parameters to make it work best. We've been able to achieve reasonably good specs, so we can get about 0.1 millimeter variance for the filament thickness, and that's helped prevent jams. We can see that that's repurposed material, and that's fresh material, and at a very superficial level, the print quality is approximately the same. And so the short version is, yes, we did it. Thank you to all the support, grant funding. We now have a pipeline. It literally took a year to get it all up and running, securing equipment, working on all the kinks and tweaking all the equipment. But we now have a pipeline, and we're in the process of getting the BDW monitors, who are volunteer students who work at the BDW to help with maintaining this particular infrastructure. We're talking with RISD, some other Brown labs, the Providence Public Library, Wheeler, with their 3D print labs and make spaces to see if we can repurpose some of their waste 3D prints, just to try to reduce just total output. And we have a lot of things we still need to do. We need to monitor system inputs and outputs. We're getting approximately like a 70 to 80% retrieval rate. Some material just gets lost. It's either contaminated or it's burnt or it just somehow magically disappears. But yeah, so it's not 100% retrieval, but it's better than just putting in landfill. So that's BDW. We're part of the precious plastic movement, and so this is the core aspect of the 3D print talk. Now we get into why this is part of the climate change and health talk, which is this. So I'm sure most of you probably heard about those giant garbage patches in the Pacific and other parts of the world. And it's not mythical, it exists. There have been imaging analyses which indicate the actual density of this material, and it's not just like floating milk jugs. I mean, it's like microplastics intermixed that have all biodegraded over the years. And so it's not going away, and it unfortunately keeps getting bigger. Humanity is producing approximately 400 million tons of plastic per year, and most of it's not going to get recycled. Approximately 10% gets recycled, 10% gets incinerated. That's 80% of 400 million tons that just goes to landfill. And I'm not going to go into all the details of how it goes into the ecosystem. It's an awful process, and Jed can speak extensively to this. But this has direct impact on us as physicians and healthcare personnel. We're now finding microplastics in human tissues. So these are some, and this is literally just hot off the press. Some of these results are coming out like March, April of this year. They've done studies looking at human placentae, and they found microplastics inside placentae, which then you could infer that there are microplastics in developing fetuses. They've also done small studies, and unfortunately these studies are like N of 10, 20. We'll get to a bigger one in just a sec, but they've looked at Saphenous venous graft harvest samples, and they found microplastics in them. And these are through mass spec, GC. These are definitely plastics, and you can see them under scanning electron microscopy. And so yes, SVGs. And those are just some examples of the plastic materials that are found in human tissues. And then this is the big one that just came out in the New England Journal about 3 weeks ago. It's a paper by Marfella, I believe. Italian study, 300 patients monitored over 3 years. They looked to see, what they did was they followed 300 people who were getting carotid endarterectomies, and then they took specimens from the endarterectomy atheromas and to see if for plastics, and I believe half of them had microplastics. The novel part was that they followed the patients for 3 years, and they were checking for hazard ratios in terms of whether the people who had microplastics in their carotids had worse outcomes compared to those who didn't. And unfortunately, it is a correlational study, of course, but it does show that there's about a 5-fold increase in endpoints of stroke, MI, and death in people who had confirmed microplastics. And there was a linear relationship in the concentration as well as with the outcomes. So unfortunately, this is an evolving thing, and it's here, and it's not going to get better for right now. So, then there's a little bit of hope. I don't want to completely end on a downer. So you've probably heard about plastic-eating microbes, and so there are actually bacteria out there that can, believably, I guess, degrade plastics. There's this one particular one that was found in a dumpster in Japan about 10 years ago, and they found that it can actually decompose plastics. And a lot of institutions are trying to engineer them so that they decompose the material faster. So, the running joke is, right now we treat people with thrombolytics and mechanical thrombectomies and things. Maybe we'll be adding a dose of plastic-eating bacteria in about 10 years, so who knows. The other, this is more the source end, separate from an entire discussion about, cutting back on 3D printing and plastic generation. This is an interesting approach, which is also biologically based. Which is adding in spores of plastic-eating bacteria, spores of those bacteria into plastics, so that when they're produced, they already contain the mechanism for their degradation. And in lab conditions, it shows that it might actually work. So I think there's a lot of effort going on into these. A lot of them won't pan out in real-world conditions, but I think there's some cause for hope. All right, so I think that's where I'm going to end. I'm going to pass off to Jed over here, and you can tell you how we're going to fix this by tomorrow.
Yeah, I don't have any slides. So.
Okay.
Can everybody hear me okay in the back? Okay. I don't have any slides. My name is Jed Thorp. I'm the Rhode Island State Director for an environmental advocacy organization called Clean Water Action. As the name would imply, most of our work is focused on water and water-related issues. We do a lot of advocacy up at the State House. A lot of our work is kind of policy and legislative in focus. I can tell you, as a group primarily concerned with water pollution, there are two emerging contaminants that keep me up at night. The first is what we call PFAS chemicals, or perfluoroalkyl substances, which many of you are probably familiar with. We're working to get PFAS out of consumer products in the state. I'm not going to talk about that this morning, but I do have a fact sheet up here if you're curious about our work on PFAS. And the other one is microplastics, because this, as Leo mentioned, is a growing problem, not just in Rhode Island, but across the world. Microplastics are defined as small pieces of plastic smaller than 5 millimeters. And there's even kind of a smaller subcategory of microplastics called nanoplastics, which are even more concerning. You have to find those under a microscope. Microplastics generally come from two different sources. There are larger plastics that enter the environment and then break down and become microplastics. So think about plastic bottles, for example, single-use food and beverage packaging, which then gets into our water bodies and breaks down into microplastics. And then there are what we call intentionally added microplastics. These are microplastics that are added to products as those really small microplastics pieces. Some of the products that contain intentionally added microplastics include some cosmetics and face washes, detergents, paints, waxes, coatings. The agricultural sector is actually believed to be perhaps the biggest source of intentionally added microplastics. Many fertilizers and seeds are coated in a thin microplastic layer, which can account for up to 50% of the intentionally added microplastics. Microplastics are everywhere. I can tell you that every water body in the state where samples have been taken, microplastics have been found. Last summer, some of you may have seen a paper that was published by researchers at URI, which found that there's now roughly 1,000 tons of microplastic in the bottom sediment in Narragansett Bay. 1,000 tons. That is a lot of microplastic. I haven't heard any solutions on how we're going to get all that microplastic out of the bay, but at the very least, we should figure out some strategies to reduce the amount of microplastic that's ending up there. What's perhaps more troubling than even the amount of microplastic in the bay is the fact that based on sort of the presence within the soil column samples that they took, we know that the rate of microplastic deposition in the bay has only been increasing in recent years. So there's been more microplastics going in the bay in the last 10 years than the 10 years before that, and so it appears to be getting exponentially worse. What is the impact on the health of the bay of all that microplastics? We know that shellfish, which are a staple item here in Rhode Island, are filter feeders. They filter out food from the bottom sediment. We know that some shellfish populations, including quahogs, have been declining. There's a legislative study commission that's been meeting over the past year to figure out why quahogs have been declining. What's the impact of all of that microplastic on these shellfish? We really don't know. Microplastics have been found in clouds, and as Leo mentioned, are being increasingly found in the human body in stool samples, lungs, placenta, and we're just now starting to understand what some of the health impacts are. Dr. Jamie Ross, also down at URI, has been doing some really interesting research on microplastics in mice. Without going into full detail, her findings are pretty concerning. Microplastics are getting into the brains of the mice and appear to be having an impact on their cognitive function and their behavior. So, what is the impact of all of that microplastic that we are all ingesting on a regular basis? So what do we do about it? I always say that good waste policy, good solid waste policy should be guided by the 3 R's: reduce, reuse, recycle. You've probably all heard those before. I like to remind folks that those 3 R's are listed in order of importance: reduce, reuse, then recycle. So recycling should be part of the equation. It's certainly better that things end up in recycling than end up buried in the landfill. But recycling is not the solution. Frankly, plastics recycling in this country has been an abysmal failure over the past 30, 40 years. We only recycle about 9% or a little less of all the plastic produced in the United States. Most of the rest of that either ends up buried in the landfill or, unfortunately, in our environment. We don't, here in Rhode Island, we have markets for number 1, number 2, and number 5 plastic, if you think about the little resin codes and the triangles. All the number 2, number 3, number 6, number 7 all gets buried in the landfill, thousands of tons of it each and every year. PVC and polystyrene are tremendously difficult to recycle. So we're not going to recycle our way out of the plastic crisis. We have to look first and foremost at reuse and then reducing the amount of this stuff that's getting into products to begin with. Plastic, as a reminder, is made from fossil fuels. The biggest projected growth sector for the fossil fuel industry over the next 20, 30 years is not liquid fuels, it's actually plastics. So I like to tell people that we're not going to solve the climate crisis unless we also solve the plastic crisis at the same time. So the extraction of fossil fuels, the refining, the transport, the production, even before that plastic ends up in the store, ends up in a product, it's an environmental disaster from cradle to grave. So we have been supporting legislation this year, which was sponsored by my friend Jennifer Boylan, who's here in the House, and Senator Sandra Cano, which we call the Microplastics Reduction Act. That would do 2 things. Number 1, it would ban the sale of intentionally added microplastics in products starting in 2028. This is similar to steps that have already been taken in the European Union. And then the second piece of the bill, which in some ways is more important than the first, it would require our state environmental agency to come up with a sampling and a testing plan for microplastics. Because despite the fact that we know there's 1,000 tons of microplastic in the bottom of the bay, we don't really know where it's coming from. Because we don't currently require any sampling of wastewater outfalls for microplastics. So how much microplastic is coming from wastewater from your house? When you rinse off that face scrub down the shower drain, how much of that is getting captured at the wastewater plant? How much of it is not getting captured? Polyester fibers in your clothing, which is a type of PET plastic. How much of that is ending up in our environment? We don't require any sampling of stormwater. So everything that goes down the street and down the drains, including tire tread. So it's estimated that up to 70% of the microplastic in the world's ocean is coming from tire tread that comes off of tires. And if you think about it, we know that tire tread goes down over time. Where does all that tire tread go? The law of conservation of matter tells us it doesn't magically disappear. It's still out there. It goes somewhere. And it's usually going down a storm drain and directly untreated into a water body. So we have to start doing some sampling and testing. We don't currently have any sort of sampling or testing protocols in the state of Rhode Island, or most states for that matter. And I would say at the very least, we need to do some sampling and testing so we can get a handle on where it's coming from so that we can then craft some smart policy solutions. I'll kind of close with the rhetorical question that I often pose to legislators, which is how much microplastic is too much before we're going to take some sort of action? Is 1,000 tons of microplastic in the bay enough? Does it need to be 2,000 or 5,000 tons before we decide to do something? Oftentimes, the pushback on microplastic testing and sampling requirements is that there's currently not a US EPA-approved testing methodology for microplastics. Plastics are complicated to test and sample for because you have not just 7 different types of plastic, there's thousands and thousands of different types of plastic polymers and combinations of chemicals that are used in plastics, which makes it a little bit hard to sample for. There are also many different sizes and shapes, but we can't let the perfect be the enemy of the good. If our friends down at URI could come up with methodologies for their study, we could copy their methodology and figure it out here. So I'll just close. If anybody would like, I do have some fact sheets up here about our microplastics bill, also about the PFAS bill. If this is something that concerns you, I would urge you to write a letter or an email to your state representative or your state senator urging them, to take some action. Because if any state should be on the front lines of figuring this out and taking action, I would argue that it should be the ocean state. So with that, I'll stop, and I'm happy to answer any questions for either me or for Leo. Yes?
I'm Sharon Rounds. I'm in the Department of Medicine, and something that has been troubling me is a lack of information on health or cell effects of microplastics. Dr. Kobayashi, you reported on that, I thought, landmark New England Journal of Medicine paper, but there's been very little, I think, research on cellular and biological effects of these materials on mammals. A lot of work on fish, corals, that sort of thing. So what governmental agency would be most likely to fund this type of research? And how can we as investigators try to stimulate funding of health effects of microplastics?
Yeah. You want to take that one, or?
Just off the hip, based on the landmark result, because there's been evidence of metabolic and reproductive harm from these microplastics for about a decade or so. But in terms of the more sexy, immediate, we have to do something right away thing, that landmark paper in the New England Journal might serve as sort of like a wake-up call for cardiovascular risk associated with these microplastics, because that's like relatively easy to treat, or at least it's. In some ways, it's just like, this like, oh, heart attack, stroke, we have to do something right now, as opposed to, fetal developmental health that's going to take 20, 30 years to manifest. So I'm wondering if cardiovascular institutes and NIH institutes might be one of the places to go.
So like the Heart Lung Blood Institute,
That's-
like the NIEHS is, I think it's one of the smaller of the institutes, actually.
Yes.
And that's the obvious one, but it would seem to me that this would affect the neurology, the brain people, the heart people, et cetera.
Yeah, and it just, I think, it's, I'm not sure, and, it's not like plastics are new. They've been around for decades and decades. So, and I'm not sure what it is that took this long to get here. Maybe it's the 1,000, tons at the bottom of the bay threshold. I'm not sure. But I think it's finally seen the light of day, and it's now becoming more prominent. And so I think, as you mentioned, it very well may affect all organs. And so it's just that the low-hanging fruit might be NHLBI, NINDS, and possibly the environmental offices.
Yeah, and it might also be worth reaching out to Dr. Jamie Ross down at URI, because the research that she's been doing on mice, she'd probably have a lot of thoughts on it too.
Thank you.
I don't know if we have time for any more questions, or feel free to grab us afterwards too. So great, thank you.